Hey, what's up, guys? Yeah, so today, I want to keep introducing the algebra, the group lecture. So previously, I already discussed the group metric exponential. So today, I want to introduce the matrix logarithm and also the Lie product formula. Okay, so this is I think the first non-trivial formula in the Lie algebra, basically some matrix algebra. Okay, so this topic is called a matrix logarithm and Lie product formula. Okay, so hope you guys subscribe to my channel. So let me just quickly say the product formula and say why we need a matrix logarithm to give you the idea of to give you the proof of the product formula. Okay, so idea is that let's consider by matrices with coefficient complex number, and the theorem says that if you do this, take m, and then go to power n, and the limit m goes to infinity, this will give you this. Okay, so this is called the Lie product formula. Okay, basically, if you know quantum mechanics or something, that people use some idea called trauterization. So for example, if you want to implement the two Hamiltonian, but you don't know how to implement this sum of it, then you can just implement a very small step. You just iterate it, separate it into power n, and go to power m, and then the m goes to infinity. But basically, the idea behind it is just this Lie product formula. Okay, so let me just give you the intuition proof. Okay, so the intuition proof is very simple. You start from this, right? So you know that you cannot there are not they generally they may not commute. So one idea is that let's write as this. Okay, so you can write as this, and then 1 plus 1 over n, and maybe plus 1 over 1 big O 1 over n. Okay, we don't care about this, and then we can collect it as 1 plus. So this one makes identity matrices, yn plus this O over. So you can see you combine this term with this term, so I can say the rest of terms 1 over m squared. Okay. Okay, then if you go to power n. Okay, so recall that you know the calculus, right? So 1 plus 1 over n, and then that n goes to infinity will give you exponential. Okay. So this means that if you go that m goes to infinity. So because this equation will give you the Taylor expansion, well, it's equivalent to give you the Taylor expansion of exponential x. So once you have exponential x, then the matrix exponential is also defined to be the Taylor expansion of matrices, right? So you just plug summation 1 over m factorial a to the something. Okay. So when m goes to infinity, then you get an exponential m x divided you can see. So for example, if you plug x to here, then you get x, right? So you get this. Okay, so basically you just times. This is x plus y, right? So m goes to infinity. This will give you exponential x plus y. Okay, so all of this proof looks very intuitive, right? Because you just take take some. But actually, it's not so rigorous, right? Because you need to deal with these terms, and maybe you need to care about why this is true. So there's some subtlety here. Okay, so today this is why within matrix logarithm. Okay, so recall that in its matrices, if A is n by n complex matrices, then you can define this is to be the a to the n factorial and from 0 to infinity. Okay, so I know previously I also proved the theorem. There's a theorem also say that if A is a general linear group, then it always can be written as exponential of something. So there's a lemma. Lemma says that one can define log of z. It's just this. So this is a natural log plus 1 z minus 1m. So this is my definition. I can define log of z to be minus 1 to m plus 1 z minus 1 to m. Okay, it's holomorphic in a circle of radius 1 about z equals to 1. Okay, so what I'm saying is that you're at 1. Okay, and I'm saying is that this log z function is well defined in here. Okay, so this is the lemma. And okay, so this is the first one. And the second one is that in this region, we always have for z minus 1 less than 1, we always have exponential log z equals to z. Okay, so z is a complex number. Okay, and so which means that okay, so 2 can be derived third. So third saying that for u with u less than log 2, and so that means that we have exponential u minus 1 less than 1, and we always have log e to u equals to u. Okay, so log is naturally exponential, the exponential function. And so the log is actually the inverse of exponential. Okay, so I think this proof is very simple. So it's like basically just using your calculus or advanced calculus. Okay, so let me just quickly give the idea. Okay, so idea is that we all know in calculus, as I say, x belongs to R. In the calculus, that for x less than 1, we always have this. Okay, you can prove this just using Taylor expansion and plus the ratio test. So you can use the ratio test and prove that x less than 1 is a converge. Is the radius 1 is a radius convergence. Okay, and then you take z to be 1 minus x. So your log z will be summation of, you just plug everything in, and you get minus 1 m plus 1 z minus 1 to m. Okay, basically this proves the results. Okay, and you can prove that since it's both log and exponential convergence, so you can plug this into this Taylor expansion and prove it's really the inverse. Okay, so now one can define the definition. So this matrix logarithm. Okay, so it's very simple that I can define a matrix log A to be summation from infinity 1 to the m minus plus 1 A minus identity A to the m. Okay, and by previous theorem, we know that if A minus 1, the norm is less than 1, then log A is well defined. Okay, so notice for some special case, right? So for only this direction is true. So notice converse is not true. Converse is not true. Okay, because so the idea is that if A minus I is nilpotent, Okay, so means that there is this k such that A minus I to the k is 0. Okay, this is stupid, right? Because if A minus I to the power k is 0, then this infinite sum must truncate it to finite sum. So we're always well defined. Okay. So yeah, this is the well defined. Okay, so there is a theorem which is very simple. So since previously we used the previous lemma, and then we can use the Weierstrass M test, so we know that log S will define. So there's a theorem says that if A minus I, so we can use two. We can use the second one to say that now exponential log A is A. Okay, and so this is, and we can use a lemma to say that let's say somebody gives you X, which is by the matrices, and the norm of X is less than log 2. then we always have exponential x minus I less than 1. And so this will give you this. So we have exponential log x equals to x. Okay. Okay. So the idea, the proof idea is basically follow this lemma, but go to the matrix, matrix version. Okay, so let me just give you the idea of the proof. So proof. This proof is a cumbersome, but just sketch. Okay, so the idea is that let's suppose this a minus identity, minus identity less than equal to less than 1. Okay, so simply when you do the proof in a linear algebra, you can assume that you first can say that A is diagonalizable and then check that where this is true. Right. So my idea is that I do the simple case. So I first suppose A is diagonalizable. Okay, so which means that I can write A to CD C inverse, where D is diagonal. Okay. Okay. So this means that this A minus I. What's going on? Okay, so this means that I can write A minus I to the power n into C1 minus I to the power n up to Zn minus I minus 1. Okay, minus 1. Okay, power n C inverse. Okay, so Z1, Zn is eigenvalue, are eigenvalues of A. Okay, so we have this, and once we have this, right, then we can just directly plug whatever I want. I can plug it. Okay, then I will get C inverse. So now every point, every one, this Z1, Z up to Zn become this series become the log, right? So become the log of Z1 up to log Zn. Okay, and both to be well defined, right? Because I define a norm to be the correct one. Okay, so this guy will be exponential C times this is just log, right? So the log of it, right? So which means what? Which means that if I do the exponential of this, I do the exponential of this log of A, I get C of log of this, right? So you can see one of Cn, which is A. Okay, so this is a proof. Okay, so conversely, you can also prove this. So this looks stupid, right? But what I'm saying is that oh, it's stupid. This is log exponential x equals x. But basically, I prove that the log and the e log a is a. We also prove that log ex x. This is another proof, but follow the same idea. Okay. Okay, and you might ask, what if a is not diagonalizable? Okay, so the short answer. So answer will be a can be approximately using a diagonalizable matrix. Okay. So what I'm saying is that if A is not diagonalizable, you can always find AN such that AN, the norm of it can be arbitrarily small and AN is diagonalizable. Okay, you can try to prove this is to be true, but this is not so difficult. You can try to prove by yourself. Okay. Okay. So now we have two. Okay. Okay. So what is our two? There's a final proposition. So this proposition says that there is a constant C such that for all unbiased matrices with complex coefficient, let's call it B, and suppose the norm of b is less than half, we have log identity plus b minus b less or equal to cb norm square. Okay, so the proof is trivial, right? Because I can just write log I plus b. I can just write log I plus b, use the Taylor expansion, and then minus b. Okay, so now simple computation will give you this minus m plus 1 b to m. Okay. Right. So this minus, so since it's minus b, right? So I'll start from 2. Okay, and this guy is bounded by what? Bounded by summation m from 2 to infinity, half, right? Half to m, and this will just be some constant c. Okay, so let's this denote this constant c. Okay, but notice that it become b squared, right? I mean I take out sorry I'm stupid. I should take out b squared. I take out b squared, this become b minus 2 and the b squared. So b squared is here. And then the rest I start from m equals to 2, right? So I can start from m to 0. M to around 1. Because I go m minus 2, right? So the first term is 2. So I can start from m to 2. But this is m minus 2. So this guy just becomes some constant. Okay, so n from 2 to infinity, 1/2 m minus 2 divided by n, and then let's call it c. So it's a cb squared. So once you combine this, then let's prove the Lie product formula. So since we have matrix logarithm, so simply speaking, when the matrix norm, when this b minus, when it's a minus I is less than or equal to 1, then we have the matrix inverse. We have the exponential inverse. Okay, so proof idea is very simple. We start from the previous one. We have this x and y, and we have this 1 plus x divided by n plus y divided by n plus this over 1m squared. Okay, so this is still true, right? Because it's just Taylor expansion. But now let's take a log. Okay. Okay, because I can choose m to be large. I can choose m to be large enough, right? Such that the norm to be arbitrarily small. So I can just take a log. And this is well defined, right? Because this m can be arbitrarily small. Okay. So I have log of this, right? Since I can take log, so I can use the Taylor expansion. So for m large enough. Okay, so now you guys see a trick. So previously, when I don't restrict the m, this log may be ill-defined. But now I take the m to be large enough. Now this log is well-defined. So it becomes this plus O of the norm of the power, the second term. Right? So it's the O of norm of everything. Square, okay? And then it's stupid, right? It's just x divided by n, y divided by m plus O over 1 over m squared. Okay, so now we have this, right? And then we can take the exponential. Okay. And then this guy must be x divided by m. Y this guy must be this, right? Because from our previous proof that the e and log are really the inverse. Okay. So we have this equals to this, and 1 over m squared. Right, so we can take m and then take m, and then m goes to infinity. So when m goes to infinity, this becomes left hand side. When it goes to infinity, this cancel. This becomes x plus y plus O 1 over m, and then m goes to infinity. We prove the result. Okay, so let me just write it down. So this our final line looks like this. Okay, and we take the power m. and then the m goes to infinity. Okay, so this looks the same as previous one, right? But we use a matrix logarithm to make the proof rigorous. Okay, so this is like the product formula. And the next time I want to introduce an idea called one parameter subgroup. And once we have this, then we can start to go to the true algebra.